We'll begin with the temperature at the top of the tower. The temperature at the top of the tower should be at or slightly above the boiling temperature of the desired overhead product at the operating pressure of the tower. If the temperature at the top of the tower is higher than it should be, more of the heavier components will vaporize and become part of the overhead product, instead of flowing down the tower as a liquid. On the other hand, if the temperature at the top of the tower is lower than it should be, less of the lighter components will vaporize. Some of the lighter components will remain as a liquid and flow down the tower. The temperature at the bottom of the tower is also important. The temperature at the bottom of the tower is usually slightly below the boiling point of the heavier component. If the temperature at the bottom of the tower is too high, more of the heavier components will vaporize and move up the tower instead of remaining as a liquid. If the temperature at the bottom of the tower is too low, less of the lighter components will vaporize and move up the tower. Another place where temperature control is important is at the feed point. The temperature at the feed point should be within the boiling range of the mixture. The temperature at the feed point should be close to the temperature of the feed tray. The temperature of the feed tray depends on its physical location in the tower. For example, the lower the feed tray is in the tower, the higher its temperature will be. If the temperature at the feed point is higher than it should be, more of the heavier components will vaporize and move up the tower instead of moving down the tower as a liquid. On the other hand, if the feed point temperature is too low, less of the lighter components will vaporize, and more lighter components will end up in the bottom of the tower. While the temperatures at various points in a distillation system are important, the relationships between the temperatures are also important. The temperature decreases as the material moves higher in the tower. The gradual decrease in temperature from the bottom of a distillation tower to the top is called the temperature gradient. The temperature gradient is measured in terms of the difference between the temperature at the bottom of the tower and the temperature at the top of the tower. In order to maintain the proper temperature gradient, temperatures at critical points in the system must be controlled. Temperatures in a distillation system are typically controlled in three ways. One way is to control the temperature of the feed mixture by using a preheater. This regulates the temperature at the feed point. At the bottom of the tower, temperature is controlled by the amount of heat that is added by the reboiler. This added heat is referred to as boil-up. The temperature at the top of the tower is controlled by the amount or the temperature of the cool liquid that's pumped back into the tower from the overhead receiver. This is called the reflux rate. Increasing the reflux rate decreases the temperature at the top of the tower. Some distillation systems contain equipment known as pump-arounds. The purpose of a pump-around is to remove hot liquid from the tower and pump it through a cooler. The cooled liquid is then reintroduced at a higher level in the tower. A pump-around helps control the temperature of the internal reflux. Since pressure affects the boiling temperature of a liquid, it's an important factor in the distillation process. If pressures in a distillation system are not correct, product purity could decrease. Tower pressure is often controlled by a pressure control valve located on the overhead receiver. This valve controls pressure by releasing vapors and any non-condensable gases that have collected in the receiver. In some cases, a vacuum system draws gases from the receiver to control tower pressure. Another pressure that's important to an operator is the tower's differential pressure. The tower's differential pressure is the difference between the pressure at the bottom of the tower and the pressure at the top of the tower. This difference in pressure is caused by the flow of vapors in the tower. Without vapor flow, there is no differential pressure. Generally, if the rate at which the vapors move up the tower decreases, the differential pressure will also decrease. And if the rate at which the vapors move up the tower increases, the differential pressure will increase. Changes in the differential pressure may indicate that a problem exists. For example, an increase in differential pressure could be an indication that the feed rate is too high. Too much feed entering the tower will overload it. If this happens, the differential pressure will increase, and the tower will be unable to make the desired separation. In this case, it might be necessary to decrease the feed rate. Now, changes in the tower's differential pressure may be caused by other problems. For example, if the differential pressure increases, the boil-up rate may be too high. In other words, the reboiler may be returning too much vapor or vapor-liquid mixture to the tower. This problem can be corrected by reducing the boil-up rate. Another problem that may affect the tower's differential pressure is a decrease in condenser efficiency. If the condenser's tubes are plugged or there's not enough cooling water flowing through the condenser's pressure will increase. As a result, the flow of vapors from the tower to the condenser will decrease, and so will the vapor flow up the tower. This means that the tower top pressure will increase, and the differential pressure will decrease. If a condenser problem is suspected, the condenser should be checked, and corrective action should be taken if necessary.